Yeah, so just going to listen in. Okay, go ahead.
John Smith, I'm with the Trout Unlimited on Madison County, and we monitor the Cayuta Creek from just above Casanova to down into the center of town in Cayuta.
I'm Deb Smith. I'm his partner with Trout Unlimited 60.
My name is John Reed, and my wife Janice Burton, and together we monitor the Upper Owego Creek, and we call ourselves Up We Go.
Bill Heaviside from the Broome County Environmental Management Council, and I monitor Bradley Creek, Little Chocoonut, and Addison Creek.
Yeah.
I'm Bill Jarvis, and this is my wife Susan, and we do a wonderful sounding creek, Whiskey Creek, in two different spots, pretty close to where Cayuta Creek goes into it, and Henry Creek. We call ourselves the Cape RedFlaggers.
I'm Ann Johnson. My husband Robert and I and Lori are Upper Cayuta Creek in Schuyler County, and we've got a little bit of Tompkins and a little bit of Shimon.
Yeah, we're the top of Cayuta Catatonk
Sorry, I just can't do this.
We do Jackson Creek, McDuffie Creek, Honey Hollow, Toffee, and Cayuta Creek, which ends up in whatever town is it.
And I'm Carrie Kerr, and I have no idea what the name of my group is. I don't pay much attention to that. But myself and several other women from the environs of Candor sample both the Wilseyville and Catatonk, practically down into Owego. Go as far south as Glenmary, which is kind of the back road of Owego.
I'm Don Sargent from Owego. Three of us monitor east and west branch of Cayuta Creek at the lower end, right near where it flows into the Susquehanna River, and then we go up. We do the east and west branch part of the lower east and west branch.
Welcome Bendigo stream loggers. Sharon, Tom, Jerry.
Great. Andrew?
What?
Come on, you're present, so.
Yeah, I go to Cornell. I'm in my second year in the planning program up there. Do a bit of real estate as well. Work for the town and county planning department, doing some natural resources planning work.
And I have to, give Andrew his due, because all of the GIS stuff that I'm able to do that you'll see today, he is a GIS master, and I wouldn't be able to do any of it without, guidance and input from him. So a lot of the work that you see that, quote, I do, comes from him. So, Steve?
And a lot of the work that, quote, I do comes from her. So I'm Steve Pennyroth. I'm the director of the Community Science Institute, and I'm really glad that you're here. We started the RedFlag program about, 2009, 8 or 9 years ago, and it's still thriving. And the long-term data sets that you all are collecting are truly extraordinary and unique. There just aren't that many long-term data sets in the state or in the country, and so Claire's going to be talking more about that.
Mm-hmm. Yeah, so I'm Claire, I'm the outreach coordinator. So the reason that we decided to do this is we just felt like you put in all of this work over these years, and it's sort of time we looked at the data in a meaningful way and just sort of share our thoughts. And so this isn't about me talking at you and sharing everything. It's a discussion. So I'm going to go through, and we're a small enough group. If you have a thought or a question, bring it up, and we can even talk about it. And so this isn't a formal presentation or anything. So I really want this to be interactive. Okay. So first of all, We're going to start out with a little parameters review. So, you all monitor 5 parameters on a monthly basis, and then some nutrient analyses every couple of years. So we're going to go over the parameters first. Then we're going to look at some trend analyses on selected streams. There are 9 sites that I looked at. 9 sites, 8 different streams. And we're going to look at some nutrient results on the map, discuss differences and changes, and discuss possible conclusions as well. So that's where the discussion part comes in. We're going to talk about the CSI Instagram, because I really want to make that happen, and you guys are really key to that. So we're going to talk about that. And then we're going to do some refresher training at the end for whoever's interested to do, ask questions, get some tips. But I'm just going to put this out there right now. You guys have way more experience doing these tests than I do. You've done them way more times. So what you've learned is valuable too. I mean, I'm not an expert by any means in these tests. I've come up with a few things that I think are valuable. And, Steve, of course, has a very long lab background, so he can offer a lot of advice too. Okay, so temperature. I know it's a super simple parameter, but it's really important, as I'm sure many of you know. It has a big impact on the health of fish and other aquatic organisms. That's why we look at it. High temperatures can endanger aquatic species that require cool temperatures, such as trout. I think we have some serious fishermen in the room right now. And high temperatures can also lead to an increase in the growth of bacteria and other microbes. So, that's just, I know temperature is a very simple thing, but it is an important one to keep track of. pH. pH is my least favorite thing because it is so, quote, simple, but yet so complicated. So it refers to the concentration of hydrogen ions, okay? And it is on a logarithmic scale. So if you got a pH of 7, a neutral pH, and a pH of 8, that is what's the word I'm looking for, Steve? A magnitude of 10 difference, okay, between those two. And that's an important thing to consider because logarithmic scales aren't exactly the most intuitive. Pure water has a pH of 7. I did confirm this with Google and with NOAA. And it's actually interesting because often when you expose just normal water to the air, the pH does go down. And that's because of the interaction with the carbon dioxide in the air. Okay, and it creates carbonic acid, yes. And that lowers the pH just a little bit. So it's rare to, get pH of 7 that's, from just a normal source that's been sitting out in the air. That's why measuring pH immediately is so important, because the holding temperature, it's 0. Because as soon as it hits contact with the air, basically that reaction starts occurring. So that's why that holding time is so short. Okay, so a water body with a pH less than 5 or greater than 9 can be unsuitable for aquatic life, depending on the species present. So again, this is really very species dependent, but even the hardiest fish are not going to do well under a pH of 3. So that sweet spot between 5 and 9, and most commonly between more like 5.5 and 8.5. But here it's actually pretty common to get pH of 8, even 8.5, just because of the natural geology and the limestone. Okay, conductivity. So conductivity is something that I'm going to be looking at a lot in this presentation. So it's a measurement of a solution's ability to conduct an electrical current. That's why you have those little meters. It is dependent on the concentration of positive and negative ions in a sample. And it does vary depending on the natural geology in the area, which you will see as we get into the different creeks, because, well, it's a surprise. You'll see later how the conductivity changes based on where the stream is. Similar with total hardness in terms of the natural variability and the geological differences, but it's primarily a concentration of calcium and magnesium cations in a sample. Mostly calcium in surface water samples. It's really calcium that you're measuring. It's so little magnesium. So those are those two parameters. And then you've got dissolved oxygen. So that's a measure of the water sample's dissolved oxygen content, as you would expect. It does vary with temperature and therefore seasonally. It's a really beautiful thing to graph because it makes this really kind of lovely little sine curve, if you will. A DO below 4.0 is an indication of anoxic conditions and unsuitable for supporting aquatic life. Again, if it can get lower than that, you know, for some species, but pretty much under 4 is not great. So you've got your chemical analyses together with these 5. You've got a relatively comprehensive water quality assessment. That's what we're going for here with your, sorry, sounds so. Okay. So, nutrients. Why did that come first? That's odd. Oh well. The things that you've been monitoring recently in the lab, the nutrients that we analyze that you sample. Total phosphorus, nitrate, nitrogen, and ammonia. So first, total phosphorus. It is the limiting nutrient for the majority of freshwater autotrophs. That's why we care so much about it. Elevated levels of phosphorus in a water body can lead to eutrophication. Is everybody familiar with that term, eutrophication? So that's when you get an overgrowth of plant matter or phytoplankton that is autotrophic, so it gets energy from the sun. And if you picture a eutrophic lake, it's a pond or a lake that is just green and guppy with algae and weeds. And that's because there's so many nutrients supporting that plant life. Now, the real problem comes when all of that plant life dies and it decays. And that chemical process of decay soaks up oxygen and creates an anoxic environment. And we already talked about how an anoxic environment is not good for the living things in the water body. So it's a very important thing to avoid. Also has harmful algal blooms, which we'll talk more about. Nitrate, nitrite, nitrogen. It's most common in fertilizers, okay? It does contribute to the growth of phytoplankton, including algae, but in a kind of complicated way, so I'm not going to get into it. And the other interesting thing is that high nitrate concentration in drinking water can cause blue baby syndrome. Anybody familiar with what that is? Ever heard the term? The reason it's called blue is because the nitrate, let's see if I can do this, the nitrate interferes with something called hemoglobin, which is in your blood. It interferes with its ability to bind oxygen to the iron in the hemoglobin molecule. And it needs to be able to bind it so that it can transport oxygen throughout the circulatory system, and if it can't, you end up not getting oxygen to the brain, hence blue. It's more of a problem for infants because infants are lacking something. Okay, yeah. So you did look it up. So it is different for adults and infants. Ammonia is a major form of nitrogen present in animal and human waste in particular, so that's why we kind of separated it out. It is a strong indicator of manure pollution, and it's toxic to aquatic life. So that's why we're looking at these 3 nutrients in particular when you guys do your nutrient sampling twice a year. But we're going to talk about that scheduling and when to do that and that sort of thing in a little bit. Okay, so let's get into the analyses. So this is the map, okay? The red dots are the red flag sites. The blue dots are our synoptic sampling sites. And the yellow are our biomonitoring sites. So what I did is I looked at 9 sets of data from 9 different sampling sites. First, West Owego Creek. I'm going to use my little flash, there it is. Okay, West Owego Creek, First Bridge. That's our first site. Next, Newtown Creek at Route 223. That's our second. Cayuta in Waverly, down here right at the border. Cayuta Public Pullout on 224. Moyer Park Candor on Catatonk Creek. Patterson Creek just below the dam. Fly Meadow Creek at Georgetown Pullover. Oriskany Creek at Lombard Road. and Limestone Creek at nil. Okay, so these are the 9 that I'm going to be, oh, did I skip one? Nope, no I didn't. So these are the 9 that I'm going to be looking at in depth, and there's some unique things about them. The reason I picked these 9, variety of reasons, just spatially diverse, data diverse. Really just thought I wanted to get a nice spread of what we're looking at as a whole. Okay, so first starting off, West Owego Creek, first bridge, the example of a pristine stream. That is a question that I asked myself starting out because it really is a very solid data set, and we'll talk about why. So what I did is I used West Owego Creek as a reference moving forward to look at the rest of the data. And what I mean by that. So first, total hardness and conductivity are correlated and seasonal. I'm saying this, and it's not just for this creek. This is a thing for all of them. You guys have probably noticed this. Who noticed this when doing their data, when looking at their data? Yeah, you'll notice that if your conductivity is kind of high, your total hardness is often kind of high. Yeah, so you're not imagining it. It's very, very much a trend, okay? And so I just want to talk a little bit about what I've done here. This is, so you've got total hardness on the x-axis, conductivity on the y-axis. And I've put a best fit line here, which is your model, right? Okay. And I just want to highlight this beautifully high R squared value right here. And what that's saying is that the model, the line that has been fit to the data, is a good explanation for the data that is available. Okay, if you had dots all over the place, the R squared would be a lot lower. Okay, so it's basically just a measurement of how tightly fitting your data is. And in this case, how tightly fitting that correlation between conductivity and total hardness is. This trend is pretty consistent with all of the streams to varying degrees. We'll see that. So that's the first observation. Second observation is the seasonality. So what I did is I created a seasonality index. And so what that means is I plotted all the points in a timeline fashion, okay, all of the sampling data for this single site, for this single stream. And I was like, I don't know if I'm going crazy, but this looks an awful lot like, like a dissolved oxygen, where it sort of like kind of went up and then down and then up and then down, but I wasn't sure. So then I created the seasonality index, and what this does is it just takes the mean of the month divided by the total mean, so for the year, okay? And so this red line here is the same as these red bars here. I know this is confusing, don't worry that much about it. But the point is that this red line here is the same as these red bars here. So that's the mean of the month divided by the mean of the total, and then it gives you this. So what this shows you is that, I'm going to call them winter months, they're not exactly winter months, but winter months, January, February, March, April, May, is June in there? Nope, March, April, May, and then December are winter months. On average, have an average below the total average, if you follow me, okay? And then our summer months, June, July, August, September, October, November, everything above the line, the one line, has an average, on the average, above the yearly average. Okay, so that's what this seasonality index, and this is going to influence my data analysis as we move on. Okay, so this is the background for that. Again, this is constant with all of the streams. I'm just using the Owego Creek one as an example. So then we look at the timeline graph, which I've doctored up a bit, and I've separated out the winter months in blue and the summer months in green. And I know it's sort of a messy, seasonality, but it's there. It's definitely there. The lines here that I've got, so you've got your black one, that's your trend line. Don't pay too much of attention to the trend line. They're there isn't a trend. It's just staying constant for this one. And then you've got your confidence interval here, 95 confidence interval, and then up here your 95% prediction interval. Your confidence interval tells you that within 95% certainty, this trend line is right. Okay? So it's hard to tell in this, but the 95% confidence intervals are actually slightly concave and convex. They are not straight lines. So you can imagine that this trend line could pivot a little bit, and it would still be right within those lines. That's the 95% confidence. The prediction intervals are different. They say that within 95% confidence that your data should lie between those two. And that drew an interesting thought for me, because this is, good data, and a lot of the dots fall outside those prediction intervals. So I'm not a statistician, but my thought is that it would be more appropriate if a sine wave were applied to this data rather than a straight line. I don't know how to do that. That is hard. But I think it would be more appropriate given the seasonality of this data. So I did the prediction intervals and the confidence intervals in a straight line. I don't know. I don't think that's really the right way to do it. So moving forward, if we were to hire a statistician, they might look at it differently. Oh, and I do just want to draw attention to the West Owego Creek catchment area, okay? And every time I go onto a new slide, do pay a bit of attention to the land use in the catchment area. So you notice this is an intermediate sized catchment area, 73.51 miles squared. And that's relatively forested. It's not the most agricultural I've ever seen. It's got little agriculture patches, but pretty average in terms of land use. So then looking at Newtown Creek, we see similar things. Okay, it almost looks like the exact same correlation graph. So again, very high R squared value. Okay, for this type of data, that's quite good. Smaller watershed, 31.6 miles squared. But again, you see that seasonality, okay? I don't think I mentioned this, but the lines, the vertical lines, those are the years. I think that's probably obvious. But so yeah, this is 1 year. So winter months, summer months. Okay, so Cayuta Creek public pullout on 2/24. So this one is interesting. So this is the largest data set that we have. It is 76 points, or points is the wrong word. It's 76 pieces of data. Okay, sample size is 76. Again, pretty high R squared value, a little bit more variation. But what's really interesting about this is that it has a statistically significant increase, okay? And that's, I don't really know what that means, but what it means is that the p-value, when you're doing statistics on these things, the p-value is less than 0.05 for this increase. And this is one of only 2 that has this statistically significant increase. But there are a lot, the regression is very complicated. This is an observation done by someone who's not a statistician, so there's nothing I can say for sure, but just me and my life statistics, this is what I found. But a lot of variables go into regression analyses. But again, we see similar things where you've got some messy seasonality, but it's there, okay? We have some really clear-cut seasonality ones later. But yeah, this one is quite special because of the statistically significant increase. This is where, go ahead.
So what you're saying is that the trend line is starting at 200 over there and it's above us, almost 250 there.
Yes.
It's above 250 there.
Yeah, above 250, 275, because this is the 300 line.
Okay, all right.
Yeah. So yeah, that increase is statistically significant. Yes.
So you said you had more data sets for this site than any other?
More like this, the sample size is 76 for this one, and that's the largest sample size we have.
Because we started 87 years ago.
Yeah, yeah.
So this is one site, but there's more tests for this site than any of the others.
Yes, yeah.
Okay.
It's one of the older groups. Yeah, that's why. Okay, and so here's where it gets interesting, and this is something that I'd like to highlight. So Cayuta Creek and Waverly is this point down here. This is the one that's at the border of New York and Pennsylvania. And I wanted to highlight this one because this is the full catchment area. This is a big catchment area. It's 138 miles squared. Much smaller data set, still high, and so that's what we're going to look at right now. So the effective sample size. So the slope of the Cayuta Creek at Waverly, this one here, is actually higher than the slope at Cayuta Creek public pullout, okay? But it is not a statistically significant increase. The likely reason is that the sample size is smaller, and that really, really affects the significance of it, because that means less sample, still a lot of variation, because this is variable data. Like it is, because of the seasonality, you know, it's kind of all over the place. It's not surprising. But yeah, the point here is that this has a larger slope. Cayuta Waverly has a larger slope than Cayuga public pullout, and yet it is not statistically significant. So it just kind of lends itself to the importance of sample size and the importance of long-term data collection and how beneficial it can be. Yeah.
Okay, so I'm understanding this, that is the increase a positive or a negative thing for the creek?
Well, I don't think you can either say it's either. I mean, I guess if you continue to do this and it continued to rise, it would be a negative thing. When you see increases in conductivity to an extreme, that's not a good thing.
It's not?
No.
Okay.
No. I don't know if it would. Yeah. I don't know if this is necessarily a bad thing. This is yeah. Go ahead, Steve.
Well, no, it just depends on what's causing that increase.
Yeah.
If it's chloride, for example, then you know that's of more concern than if it were just you know, calcium. Maybe something's going on with the groundwater, more leaching of calcium and so on.
Yeah.
But if it's chloride, I mean that's of course something we can call.
Mm-hmm.
And we are seeing chloride increases in some Cayuga Lake watershed.
Yeah.
Okay.
Yeah.
Was the summer of 15 the drought year?
Was it, or is it somewhere
Yeah.
since 2016?
It might have been 16.
I think it was 16 because I graduated in 16. So.
Okay, because I saw a lot of spikes in the summer of 15, and I wondered if that was due to drought. Because I would think drought, you'd have a little rise in conductivity, right?
Steve, what do you think?
Not necessarily?
You know, I mean, that would, I mean, the conductivity is a reflection of the groundwater. So as long as the stream is flowing, okay, it's not, if the stream was standing, you're just sitting there, standing still, and you've got evaporation, then yeah, I mean, the conductivity would go up. But if it's not standing still, okay, if it's constantly being replenished by groundwater, then it wouldn't necessarily go up.
Okay. So next is Catatonk Creek, Moyer Park, Candor. Okay, so this one is also a little interesting because it also has a statistically significant increase. Okay, and again, 0.83 for the R squared, still pretty good. You know, we're very much in the realm of solid R square values, so that's fantastic. For the correlation anyway. And so then when we look at this with the statistically significant increase, but the difference with this data set here is that there's a lot more, quote, summer months than the winter months, so the seasonality isn't quite being as well expressed as in other data sets. Didn't think that was going to make a difference. But then when I found out about this seasonality, it does look like sampling in the winter in addition to the summer. You know, it does paint a better picture in terms of the data set.